I would like to introduce Stefanie. She's just getting plugged in at the moment. Hi, Stefanie. Okay, so this is Stefanie, and she is going to be telling us about Datamorph, a cautionary tale of summary statistics. Take it away.
No. Okay, so I'm going to stay over here then. Okay. All right, sorry about that, everyone. Last minute change here, and I've been having computer problems last night. So I'm here to talk to you about a personal project of mine called Datamorph. And particularly, it's about how you have to be very careful when you use summary statistics. So a little bit about me before we get started. So I'm a software engineer and data scientist at Bloomberg in New York City. I'm also the co-chair and founding member of Bloomberg's data science community. I'm the author of A Hands-on Data Analysis with Pandas, which is a very big book on pandas, which I gave out to some attendees yesterday to weigh them down on their flights back. I did my undergrad at Columbia University in operations research, and then I did my master's in computer science from Georgia Tech just recently. So, to the main event. Summary statistics are not enough, okay? So if we look at these three data sets, right, they are very, very clearly different. If someone tried to tell you they were different, you'd probably call them crazy, right? Or sorry, that they're not different, right? But the thing is that if we only looked at the summary statistics and never actually visualized them, they would be exactly the same. So they have the exact same mean in both x and y. They have the same standard deviation in x and y, and they also have the same Pearson correlation coefficient. And so what we actually need in order to be able to distinguish from these at a statistical level is to look at what are called moments, okay? And this is a statistical concept that perhaps many people aren't super familiar with, but the first moment is actually the center of mass of our distribution, or what we would call the mean. In this particular case, these are central moments, so we're removing the mean from it, so that puts the first moment at 0, etc. So that means that our second moment is then our variance. And then when we get to the third moment, as you can see, if we're just looking at, so right here, the third moment is actually where we start to see the change. Okay, the third moment is the skew of the distribution. So if we just take those same plots, and then we now add marginal distributions, those histograms in both x and y, you now see that, again, there's clear differences in those distributions that were not being captured by those summary statistics that we saw before. But once we add in that skewness in x and y, which is the asymmetry at the tails of the distribution, so let's see if this, no, the pointer doesn't work, but so that would be, can you see? Yeah, so like over here, the symmetry over here versus something like over here, okay? And then you also have the fourth moment, which is the kurtosis, and that's the weight at the tail, so how much is actually in those tails. And then you can clearly see that now there's differences at that level. And now when we go to those statistics, we then have another problem, right? Now we're isolating just x and we're isolating just y, right? And so coming back to that correlation, we have to be very careful with that for multiple reasons, right? In this case, all of these are indicating no correlation between x and y, right? That's fine. But our correlation coefficient is measuring, in this case, linear correlation, okay? And if we don't actually visualize, we potentially fall into another big trap. And here's what's a popular data set called Anscombe's Quartet, which was made back in 1973. And you can see that it shares the same properties as those three we were looking at before, where the x and y means, the x and y standard deviations, and the Pearson correlation coefficient are the same across all four. These were constructed by hand, so they're a lot more simple looking to make sure that they fit with that criteria. But if you notice, only the one at 1 and 3 are actually linear relationships. But all of them have a strong positive linear correlation, right? 0.82. So we have to be very careful when we just look at that as a summary statistic, because we actually can't even say, like, look at the second one. That's definitely not linear, right? But if we just saw that number, we're like, oh, great, we have a good linear correlation here. So you absolutely must visualize, and you have to use that in context with those statistics that you have. And despite all of this, despite this being in 1973, this is still a problem we continue to have. People don't want to visualize. It's a lot harder than just calculating a statistic. And so we end up, this is going to repeat and repeat and repeat. So people, including myself, have tried to find ways to make this a little bit more memorable. So one particular example in 2017 is from researchers at Autodesk. They created what's called the Datasaurus dozen. So if you look at the top, they start out with this dinosaur called the Datasaurus, and then they use what's called simulated annealing to push the points around to get other shapes. So if we look here, for example, this dinosaur and this star have the same mean in x and y, the same standard deviation in x and y, and also the same Pearson correlation coefficient, right? But now we have another problem. But also, the one thing they added here also, I forgot to mention, is that they introduced the animation of this. So it's not just the dinosaur and the star that share those summary statistics. It's actually every single distribution of points that you encounter along the way as you transform from one shape into the other, which is actually even more than that, because this is randomly moving the points around. So that means there's actually an infinite number of distributions of these points that share these summary statistics. So you really gain nothing by just showing those summary statistics. It's not telling you really anything. And now we have this new problem. What's so special about that Datasaurus, that dinosaur, right? People now seem to attribute this concept to, oh, there's something special about the way that dinosaur is designed, because they think maybe of Anscombe's quartet, how you just carefully moved one point off and that made all the magic happen, right? But there's actually nothing special about that Datasaurus. And so that was my motivation for why I built Datamorph, right? The idea that dispelling the myth that it's not just the Datasaurus, it's anything, right? And also as something that the more repetition you have with something, the better it sticks. So the more times you see, oh, it's not just this dinosaur, it's also a panda and a sheep and a set of music notes and the Python logo, as we'll see in a bit. And this is why I built Datamorph. So in particular, I'm addressing several what I see as limitations in those previous approaches to this. So the first thing is that this is actually an installable Python package that can be used. So you don't have to go hunt down code from some researchers and then hack away at it and try to figure out what it's doing in order to get it to work. You get animated results right out of the box. So you get from the morphing, say, from the dinosaur into your star and then back into the dinosaur. I also added in several additional data sets so that you have additional things to start with instead of just the dinosaur. But you can actually also use any data set that you want. So you can just generate a CSV of x and y points and some shape that means something to you, and then you can work on transforming it into other shapes and really convince yourself that this is the case. I'll talk a little bit about how some shapes work better than others, but that's a thing we'll get to later. And it also makes this, again, easier for people to experiment on their own data sets. So maybe you just think now this is a trick of various shapes, right? So if you took your own data set, you'll see that this is also the case. And then also, finally, that this now makes it possible to have an infinite number of examples to show this concept, right? You're not limited to dinosaur to circle or whatever. You can design whatever you wish to transform. So here's an example of how that works. Since we all love Python here, we've converted the Python logo into a heart, preserving the summary statistics, right? And you can see that at the whole point, at every single point as those points are moving, those summary statistics have stayed the same, in this case, the 2 digits of significance. And so here's the code that I used to make that example. Once we have this package, all you have to do is install it. It's available on PyPI and Conda Forge. And then it comes with an entry point, so all you have to do is use the entry point. You say which shape you're starting with. In this case, I'm starting with the Python logo, and which shape you want to convert into. In this case, it was the heart. So here's a little bit of a look at what's going on behind the scenes. A simplified example, but the notion that taking what the researchers had as one big monolithic file and actually using classes behind that. So we have, in this case, 3 main classes here. We have our data loader, which can pull in the Python logo dataset or a dataset of your choosing, convert that into an internal class. So it's essentially, we'll talk about it a little bit, it's essentially a pandas data frame with some extra functionality that makes the morphing work. We also have the morpher that actually does the morphing, and then the shape factory, which is creating the target shapes based on the data. And that's the key concept of why this works for anything, is because we're using attributes and information from our data set to determine what we can morph it into. So breaking this down, if we just look at the data set, what data morph is doing is it's reading in the data, as we were with pandas, right? But then it has to calculate, one big thing is these bounds you can see on the screen. So the innermost bound, the dark blue bound, are the bounds of the data, okay? So the bounds of the data are how far in each direction, x and y, are we going. So you can see it's a tight bounding box around the data, right? The red one, the middle bound, are the morph bounds. That tells the algorithm how far it can push the points away from the shape. You don't want to go too far because then you risk them not being able to come back and actually fit to the target shape. So it just gives them some bounds to their movement. And then the final bound, the outer one, are the plot bounds. And that helps us determine where we're actually going to be plotting each frame of the animation. If you don't do that, you end up moving around as you do it, and you want to have a consistent thing where it looks like the points are moving and not the frame of your plot, which would be distracting. And also what this actually provides is that this helps get rid of all the need for hard coding, right? So in the initial code that the researchers had, they're hard coding what the mean in x and y of that dinosaur is. And so if you want to take a circle, it's using hard-coded values. So you have to find heuristics and ways that you can use what's information you have from the data in order to determine how your target shape should be. And that's what these bounds allow. And so here's just an example of some of the data sets that I've included in there already. And I've made 2 releases, so I make a point to add some fun new shapes each time. But you can see that all of these work. So it's not just a dinosaur, right? You can see we have these variety of shapes, and also anything you can come up with. So please try and send me something. I'd be happy to see what you come up with. I think the hardest point is actually making the points of the shape that you want. I do have a piece in the documentation on how you can do that if you're interested. So let's move on to creating our target shape based on the data. Okay? And so what I mean by that is that, yeah, I want to convert the Python logo into a heart or into a star or a circle. Some of these have equations, right? Like a circle, you have a specific equation for it. The heart is actually a trigonometric equation, which is quite interesting in itself. But something like the star, you're kind of figuring out, based on information in the data, where you should place the points of the star, and then you're just using line segments to connect them, right? So what you need to do is you need to figure out per data set. So you see the ones on the top are on top of the Python logo, and the ones on the bottom are fit to the music notes data set. And so you can see that the heart actually is a different dimension, and it's at a different spot in the XY plane compared to those two. And that's because it's using information that comes from the data set, right? To figure out where it should be located in XY plane, that's the translation. And then also how big or how small should it be. So that's the scaling of the object. And that's all done using those bounds and sometimes some statistics coming off of the data itself. And here's also a listing of what I have so far as the initial shapes. So I went through the initial research from Autodesk, and I expanded all those shapes to work in general. So you have all of those, and then you have additional shapes like the heart that I've added. So I have the diamond as well. I want to do a club and spades to finish out the suits, but those are significantly more complex. So it's a fun little math problems every time you want to add a shape. And so since we're at a Python conference here, we'll talk a little bit about how this actually all happens. So in the initial code base from the researchers, the code for determining which shape you do and actually what it means for a shape to be a shape is actually just one giant if-else statement. And so that's obviously very hard to maintain. And even there's a lot of logic that's actually common across all of these things, what we would call a shape. So what I have here is I made this hierarchy. This is a simplified version of these classes. So we have an abstract class at the top. That's up here. This is our shape class. So this defines what does it mean to be a shape, okay? So a shape has to be able to do 2 things I have up there. One is if I give it a point, it needs to be able to tell me how far away that point is from it, so defining some sort of distance metric. And it also needs to be able to plot itself so that we can actually visualize it. So once you have that, then it's a matter of coming up with categories of shapes. So a circle, right, has an equation. So that's kind of its own category right there. And then a circle has properties like where is its center point, x and y, what's its radius. And then something like the rings, right, which was the concentric circles, that is just composed of different circles, and you just have to see which circle are you most close to, and that's your distance metric. So in some cases you need to override like that, and other times with the case of a line collection, it's just shapes that are made up of many lines. The lines can be in any orientation. They can be connecting. They don't have to be connecting. And so we have things like the diamond, the slant up lines that we saw in the previous slides, and also the star, and a lot more fall into this category. And then we have the other one, which is points. Sometimes it's not easy to have an equation that also defines a distance, and they're not straight lines. So points, something like the heart, you might use a trigonometric equation to generate the points, and maybe you just sample it across some range, and then you can scale. There's a balance between having a lot of points to fill out that thing and having something that at least just looks like the shape. If you have too many points, you slow down the whole calculation because you're now calculating the distance to every one of those points. And finally, in the process, then we have our actual morphing of the data set into that target shape. And this is what's done mostly from the original research. This uses a process called simulated annealing. Okay? So at each iteration, we run for a given number of iterations. We select a point at random, and that's when it shows up in blue over here. And then we move it a random amount to a new location that still preserves our summary statistics to 2 decimal points, or you can customize that as well. So as long as it preserves that, we're moving it. And you see, once it's moved, it becomes the red point. So you can see, if you look on the right, it's sometimes moving them closer to that heart shape, but it actually sometimes moves it away. And this is actually very necessary, because if we don't do this, you could potentially end up in a situation where you can't recover from, or your points they clump all in one spot, or they've picked a bad random direction, and now you have problems. So avoiding local optima by doing this allows you to have a potential to recover from a misstep. You still make sure you don't move it too far that you no longer have your summary statistics preserved. But you sometimes move it away. And so you can see all in these examples, you're moving it away or out of the range of the heart when there was clearly a better choice. And the likelihood that you do this does decrease over time, right? Because you don't want to allow this to continue going away, because then you'll actually never get to your target shape. So this decreases using what's called the temperature in the simulated annealing process. And you can see that regardless of the number of iterations that we run, we are decreasing this, and we end up at the end towards 0. One of the changes I made to this algorithm is then also decreasing that point movement over time. So if you notice in the beginning, it looks like the points are rushing away very quickly to form to the new shape, and then they slow down. I think it just has a nicer visual effect. And this is something that does decay over time as well. Again, we don't want the points moving big amounts later on. We want to have them closing in on their target shape. So this also decreases. But it does not drop to 0, because if it did, then again, we would get stuck where the points weren't moving. So really quickly, I'll talk about some of the limitations of this and areas that I want to work on in the future. So one big one I see are bald spots, right? So you can see here that on the left is what we would actually like. We convert the dinosaur faded in the background into that heart shape, which looks pristine. What actually ends up happening is on the right. So the grayed out portion is where we actually don't end up with any points to fill the heart. And so right now, the distance metric doesn't incentivize the points not to clump, and so you get this behavior. Wherever it happens to be close, they move and they're happy. And it's not enough. The next thing is the morphing direction. So I mentioned the need to take a data set and then morph into a shape, right? But in theory, it would be nice to go from data set to data set. So maybe panda to dinosaur, or shape to shape, maybe heart to diamond. It's definitely possible, but it requires a little more thought on those angles. Another thing is speed. So I mentioned before, being very careful with that distance metric. You're doing one point to all the other points in the shape, which can be a lot of processing, and then you're running this for 100,000 iterations. Right now, the algorithm is not vectorized, and that was basically inherited from the initial code base. It's not trivial to vectorize it because of the sequential nature of it. So some thought has to be done there as well. Another interesting thing is that the scale of the data will affect your morphing time. So here I have the dinosaur. In the middle is the one that is in the package, and the one on the left is scaled down to half size, and the one on the right is scaled up double size. And the half size one converges to the shape in about half the iterations as the main one-to-one size. When you double the size, you end up getting a 50% increase as well. So you can see that it clearly affects, and this is because of that, how much you can move the point. And it's not, again, it's not as trivial as just, we'll just move the point more at each iteration, because then you end up in other problems. So this is another problem to tackle as well. The convergence is also something. So I mentioned before that we run for a certain number of iterations, but you might get to the end of the iterations and you realize, actually, this wasn't enough. This heart doesn't fully converge, so you need to run it for more. Or conversely, you actually ran it for too many, and now the points have just been dancing around the heart for 10,000, 15,000 iterations. And so that's wasted time in your animation that you then have to clip. So the idea would be to have the shape or have the logic recognize somehow that it's getting closer and have some kind of early stopping criteria so that you could still provide the number of iterations, but stop if you've already reached your target. And a little bit on the lessons that I've learned while doing this. One, repeating research is hard. So I mentioned that my first step was to take the Autodesk researcher's code and recreate just the actual data source to the circle, which was in their paper, right? And figure out how the code was working. And this was still very hard, right? Because the code that they provided was not necessarily the code that was in the paper. It was some subset. It had things missing, things that weren't documented, weird variable names. And so just hacking around at that took about 4 hours to reproduce what they had. And then extending the research is even harder once you get to that point. So I then made my panda shape, right? And then I wanted to get that to work with this data source, the code that they had. So I actually made sure that my panda shape had similar summary statistics to the panda, to the data set, the data source, so that it would actually somewhat match the code that they have, and I can see if it was, how I would actually go about doing that. And again, it's kind of the same problems, those hard-coded values, the partial code base. So this took almost 2 days just to get that to work for a different data set that was almost exactly the same in the summary statistics. And then from there it was going back through and actually, well, can I change the panda? Can I actually make it in a different spot in the distribution? Can I change the X and Y? And so then I went on to actually building and distributing the package. And this was very interesting because this is something that usually when you work internally on something, you maybe don't actually see the full scope of what goes on in the open source world, like what it takes for someone to distribute a package, build a documentation. So this is really eye-opening for me because I realized this could be a good teaching tool and just fun to play around with. And I personally learned a lot from just building this. And so a lot of challenges here were cleaning up that monolithic code base and actually applying good software engineering principles, using classes and modular code and properly documenting things. I ended up building a pre-commit hook to validate my doc strings because I wanted to be very good and about having doc strings everywhere. And that's actually available in NumPy doc right now. Creating a robust test suite from scratch, building documentation, and then actually going about publishing it. So that took about 2 months from that point. So huge jump in the amount of time there. And so then I would say that the final thing that I have on this is just you have to be very, very careful about trusting docs. Because some of the things that I bumped into that really had me bashing my head for a while were actually just errors in upstream documentation. I fixed them for y'all, so don't worry. But definitely be aware that sometimes it's not you, it's them. And so here I just have some helpful resources that I consulted while going along for the parts that I wasn't too familiar with. And the closing remarks, summary statistics are not enough. You must visualize and use that in context. And then definitely try out Datamorph. That's how you can install. Thanks, I know we're almost at time, but a quick question.
Okay, so Stefanie, thank you so much for the impromptu start to your talk. And also, it's as if everything that could have gone wrong went
Always.
wrong, and then we had the aircon starting and
I
everything
know.
like that. So many congratulations for dealing with all of this under such difficult circumstances. I can see we have 11, oh no, now they're changing everything. We had 11 seconds left, so I guess we haven't got a chance.
I think we had one question.
We had one question? We'll have one question.
question.
This is a quick question, so you've got 10 seconds and I'm grabbing this from you, okay?
Okay, so my question is, I just installed dataset in Google Colab, and when I find there is an issue, I checked in ChatGPT, but ChatGPT is not trained by 2021. If I find any error in dataset, how can I check my error through any link, any alternatives other than ChatGPT?
It's not going to be in ChatGPT. This is new, right? So ChatGPT does not know about this, but it's on GitHub. So you just report an issue on GitHub.
Okay. Thank you very much. Another round of applause, please.